So as Nikhil introduced on the beginning, we will touch today the whole points of the well completion design of the wells. I used to call it the initial completion design because this is our first after the drilling project was launched, which need to be planned. So we'll go through the well life process. How is important that we complete our wells and design our completion for the whole well life, if we can, and which is the well design process where the completion engineer involvement comes and what are the rules and responsibilities. Also, we will go through the details inputs which well completion engineer need to get in touch with the different stakeholders. What are the inputs which and from which he is gathering all the information and making a decision for the, let's say, proposed completion design, and what are the deliverables through the well completion outputs. What are the documents and simulations and things which he need to deliver during the process of, let's say, the well design. We know that the well design process in the many companies are pretty much similar. We are going through the gate processes where from the beginning to the before the execution phase, we need basically to design our completion fit to purpose, which need to be technically, economically approved. After which we will have a green light for the process to ordering the stuff and to execute and complete well and produce on the end. So let's go to the journey of the well completion engineer. And let's say that the first column, which I will say the basic one, is let's look how the one of the well life and the one well let's say process from the beginning to the end looks like. So when we decide to drill the well, we have this exploration and reservoir engineering researches, which I put approximately time, is not meant to be exactly, but approximately how much months we need to prepare or weeks for the each phases. So on the beginning, the reservoir guys, we look into it, into 3D seismic and the seismic, and to try to figure out where are the potential and the well location will be the best one for reaching the hydrocarbons. After that, we are going to the process of drilling, which can take, I put approximately 2 to 3 weeks, but if we are going deeper, then can take months or two. Where the initial completion after we finalize the drilling can take up to 5 days, depending on the complexity. And you can see now the whole production of the well will take so many years after we finalize, let's say, the well. Everybody looking on the drilling as the most exciting the process, but as you can see, the whole well life cycle, the drilling is really short period and initial completion, where we need to complete the well and answer all requirements needed for the whole well life. So before we come to the plug and abandon. So in the whole well life, as I mentioned, we have well construction phase where we are, as a completion engineer, focused to deliver together with other stakeholders, drilling engineer, reservoir, production engineer, to build the well, which will produce for so many years. Yeah. So during the second phase of the well life, which I call it the phase where we have a lot of workovers and well intervention, depending on how many zones we will produce in the well life, we will have a lot of activities like a well intervention, well recompletion, and again, well intervention for the, let's say, some logging, some coil tubing jobs. In the certain point of the well, we might have some needs for the stimulation job, like acid stimulation or high pressure stimulation, until our production depleted so much that we don't have any more natural flow, and then we will switch to the artificial lift and plug and abandon. I took this example like on the one natural flowing early stage well. So coming from the natural flow to the artificial lift and the plug and abandon, when basically we don't have anything more to produce. So you can see in this whole well life, The well completion I marked here as an icon, which basically interfere and communicate with all the stakeholders during the well life, because we constantly need to pull out the initial completion and put another one which need to fulfill some requirements in that moment, depending on the information which we are gathering from production. So let's start from the well-design process, from the early beginning. Yeah, and you can see on this picture, I illustrate that completion engineer basically will communicate in this period with a lot of stakeholders, which I considering in the whole well-design process journey, you have so many people to basically fulfill their requirements, put everything in one package and deliver like completion design. So as I mentioned earlier, we have the process which from drilling a new wells from the beginning to the end will looks like basically, I think in 99% of the companies like this. So we have the plan to drill the well, we have identify phase, select phase, define, and execute our work. And on the end, we need to hand over our product to the, let's say, to the asset production as a final stakeholders and leave them to produce the well. After which, if they have any problem, they will come again to the well completion engineer to be able to design recompletion. So let's go one by one. So in the moment when we plan to drill the well, as I mentioned earlier, we will focus and the reservoir engineer, petrophysics, geologists will focus on opportunities, which can be exploration, appraisal, or development well. So in this early stage of the project, they are focused on predicting the production forecast, how much this well are potentially to produce in order to quantify how much they expect hydrocarbons in place. In the second stage, which sometimes is the stage of no go or go for the project, we have already developed production profile, expected production rate, estimation of reserves, well potential to flow, and drilling and completion feasibility. So in that moment, we already know that we might have something economically worth to produce, where we have the preliminary design for the drilling and completion to see if we can somehow answer all these requirements. For the next stage, if we have a green light in identify phase, meaning that the well, the drill and equip will be economical, looking on production estimation rate, we are gathering this multidisciplinary team together. And this is the point when I said so many stakeholders will join us. So in the multidisciplinary team, we have to deliver a final drilling program, and we need to come with the conceptual completion design. In that moment, we are all already discussing together with production technology discipline as artificial lift, sand control, flow assurance, stimulation. So we need all this information in order to come with some conceptual design, for which in that moment we need technical and economical proposal together to deliver. Yeah, this is the early stage where we select which type of the wells we will drill, which type of the completion need to be implemented. And on this point, we are really having a huge interaction with the reservoir engineers in order to understand how I call it the reservoir completion. Interaction with the reservoir in the wellbore, how we will try to complete and interact with the reservoir. Which I will speak later on, but at this moment we already have a green light to drill the well, but then we need to have like on one place so many engineers to work together. I will explain later how this works and how from the position of the completion engineer looking in the reality. Yeah. So in this select phase, we select the type, as I mentioned, and then we are going to the much more detailed deliveries. Yeah, so in this moment, every one of the engineers involved in a project need to bring the final design. So let's say for the drilling engineers, they need to already compile the final casing design trajectory for the whole well, which drilling tools, fluid strategies, logging, and so on need to be finalized in that phase. For the completion engineer, market here is a blue color. I would say that the completion engineer in this phase have several deliverables, from which the most important are stated here. So he need to come with the well completion tool selection, which kind of the completion tools need to be in completion in order to answer all the requirements from Reservoir, from production engineer. Tubing stress analysis and tubing selection and design. In that moment, these first, let's say, two deliverables are coming together because we are compiling tubing, packer, and other completion tools in one system, in which completion engineer need to verify using different softwares which are on the market, but basically need to deliver tubing and let's say jewelry, packer, and completion tools which will work together for different scenarios in front of the well life. So when he designed the one completion, he is not looking only on production phase. He is looking in the potentially acidizing job, potential injection job, killing the well, leak occasions, and so on. So there's many other scenarios which he needs to include in his design to see if all this system will work under different circumstances. Then he will be in charge also for the completion fluid selection, for the metallurgy selection, for the Christmas tree selection, perforating design, well barrier design, and on the end, all of these need to come together in the well completion program as a final product of defined phase. With final product, as I said, the well completion design will compile all of these. Plus, we'll considering also detailed operational program for the completion phase. In this phase, if everything is verified and signed, we can go to execute. So before we go to execute from the define phase and execute phase, we basically need to include time for the deliverables. Yeah, deliverables in terms of delivery time for the completion tool, delivery time for the casing tubulars, for the tubing, and so on. So whatever we agree on the define phase, we need time. So this delivery, just to taking as an example, the completion tools delivery time is approximately from 20 to 25 weeks. For the Christmas tree, if we have a contract already with the supplier, this time can be also meeting 6 months, but in some cases, if we are going beyond our standard stuff, can go up to 1 year, depending on the metallurgy, depending on the pressure rating and the system complexity. So whenever we in define phase finalize this, we are in the process to execute, but we need to wait until all these completion tools and the drilling tools and the tubulars comes. We are in execute phase right now, where I focus only on the completion engineer, and his role here in execute phase is the field supervision and support. It's not always the case that the completion engineer will go on the field and supervise the job. In some companies, completion engineer will stay in the headquarters and technically support execute phase, meaning all collaboration with the service company who provide completion tools, who provide the tubulars or any other services as a perforation services or slick line coil tubing services included in the completion program. He will be the focal point, and he will be a single point of contact for this. In some cases, he will be present on the location in order maybe to supervise the job, but as I said, is not the case all the time. After we execute the job, meaning that we finalize the well, we drill the well, complete the well, we need to deliver all the, let's say, documentation in a one, let's say, package, which we call it the well handover document. And final well report. All together with the drilling, we compile one file, which we handed over to the asset, which will produce the well further on. So in that moment, we have finalized the product as a new well and then give to the production who will produce the well, and they know the procedure for starting up and so on, hooking up the well and producing. So as I mentioned here, they will do the well monitoring, and in the future well life, in case that they need to do any kind of well intervention which will require really stress on tubulars and the completion tools, they will come back to the completion engineer to design again scenario under which they want to maybe to stimulate the well or to inject something or to kill the well or to do any other jobs which can affect maybe completion tools. So this is the journey which every, let's say, participants in the building up the new well will pass together, and on the end deliver a final product. I will move for the next one. So just to give you an overview, there are in this process not only the engineers involved, but as you can see, we have like a project management, we have a service company supporting us with their products and to interact in order, example, for the completion engineer to put operational steps, example, the packer setting procedures, the perforation procedures, coil tubing procedures, anything which are specific for the service company. We are collaborate together with them in order to compile one final well completion program. We interact and have very close to us production technology engineers, as I mentioned, artificial lift if it's needed, or cell control, flow assurance, simulation. I will explain later why they are very key player in the completion engineer role. We have geologists, petrophysicists, geophysicists, flow assurance specialists for the metallurgy and chemicals. Very often we have reservoir procurement and technical authority as a, let's say, authority in the company who will give us a green light for our, let's say, work prepared as a highest authority. So let's look a little bit and on the, let's say, the life of the well completion engineer, how his life looking when he got a proposal for the new well to be drilled. Yeah. So in the beginning, he don't have so much information. Only if this well will be positive to produce, initial flowing rate, and so on. So in that moment, he need to think about the initial completion design, but conceptual design, to not go to too much details until he can have some high-level estimation for the technical and the budgetary proposal for his design. So what he need to look on the beginning. The first question for any completion engineer will be, what is about this well? Is exploration well, appraisal, development? If it's a development, it's a little bit easier because he can look around on the field, the nearby wells, and to compare how we complete the nearby wells, how those wells produce up to now, did they have any issue? Because all this valuable information can help him to compile, to avoid any mistake made before in the past, and to improve design in the future. So he is looking like reservoir interaction. Did he need any sand control if the example reservoir is not consolidated, or if the reservoir pressure is below hydrostatic, is already depleted, maybe he need artificial lift from the beginning. As I said, all of these components, and especially if we need some stimulation job, his focus then to highlight and to get closer to the responsible engineer, stimulation, sand control, or artificial lift. So I put the list of the inputs, which I think they are valuable, but they are not need to be followed with the numbers. So I just listed them. There is a, let's say, 8 different inputs from which we will shape our completion design, but they are not executed one by one. Very often, you need to go through all of them and then come back again, interact 2 of them with one in terms of communication between reservoir engineer, stimulation engineer, artificial lift, and bring them all together in order to find out what are the really detailed information about the reservoir, how this will interact with our design, what we need to include, bringing up the metallurgy specialists, bringing up the flow assurance specialists, in order to see if we have any issues producing this fluid and hydrocarbons. So let's go through all of them, and I will give you a little bit overview on what I'm looking for when I start designing the well, which the key components are very tricky and important for me in order to verify my path until I come to the final design. Sometimes you can work on your design, but one component, one requirement can bring you back to the table to start from scratch. Yeah, because whatever we have as a target to produce the well, whatever we design, we need to see if this design can fit inside the drilling design. If the drillers design the small tubulars that we cannot introduce, example, the ESP pump in the region where need to be placed, we need to come back to their desk and ask them to redesign the drilling design, basically to enlarge in order to supply, example, ESP pump to achieve the production rate which we promise. Yeah. So this one is really a job with a lot of interaction, a lot of work which we need to redone again, including new fresh information. Sometimes the new information comes on the way, and then we need to adjust. Yeah. Many times we need to compromise something, and then we need to get a green light from specific engineer if we want to optimize a little bit design in order to fit all together. That this is why I said we need to compromise something. Maybe we cannot produce in such a rate because we are limited with something that we cannot achieve. So this is like a play where you need, as I said, too many interaction, too many tasks will come on your desk that you need to compile and build something fit to purpose. For the well type and reservoir info, really basic one, and I think that the first one which you need to gather information is in general, as I said, if this is the exploration, appraisal, development well, or this will be a producer or some injector well, can be CO2 injection, polymer injection, the wastewater injection, and so on. So you need the basic thing in your head, which of the wells will be drilled. As I said, the exploration well have a different targets. We need to drill across the reservoir. We need to maybe discover something new. This is called exploration, to explore something for which we will not turn this well into production. We just need to obtain some information, and our target is to reach the depth and then maybe to test different formation of which we set as a target. And after that, the well need to be plug and abandon. When we have this in our head, we can easily shape our completion. We will not spend too much on the longevity, but we will put very short production completion with not so fancy metallurgy, but we will probably answer all requirements in terms of testing and then plug and abandon afterwards. When we are talking about the fluid type, we need to know which kind of the produced fluid type we will put inside, example, our tubulars, our completion tools. Really important in this segment is to to know if we have H2S, CO2, some aggressive environment in order to tackle this issue. We need to know, example, if there will be an injector well, what we are injecting in order also to mitigate some corrosion, some damage of the pipe, and to give them a longer life. Basically, also you can look in this moment, very critical one is this well will be produced by natural flow or artificial lift, or you need to combine the first year or year and a half, two will be natural flow, but due to the very expensive workover, you want to compile two systems together and put them initially that you can produce naturally, but when well deplete very fast, that you can switch on some sort of artificial lift. If you are going, let's say, for the standard completion, very, let's say, medium to low shallow wells, then will be a little bit easier. But if you have very challenging wells where we have HPHT wells, high pressure, high temperature, that we have a sour service environment, plus if we need any kind of the sand control and stimulation job, you can see how much you are going up with your details. In fact, then this complicates your design. And on the end, you just need to pay attention on the details. For me, I would say even the smallest well can bring a lot of headache, but the big wells, deep wells, need really a lot of attention, paying attention on the details, on the every component, to not be compromised so much if we need to compromise. The well trajectory is purely coming from drilling, and what will influence completion? This is the question what completion engineer will say. So here we have some illustration how this trajectory can looks like. Yeah. The first one, number one, you can see that it's a straight vertical well where the completion can be straightforward. We don't have a dog legs, we don't have any risky moments on the trajectory where we need to pay attention if our tools can be deployed or not. Number two, we have a slightly deviated well, which also until 45, 60 degrees will not complicate our life. Above 60 degrees can be very difficult to operate with a wireline or slick line. So this need to be taken in consideration. If we have a S shape, like a number three, then we need to pay attention. There will be tools going basically through the well pad and need to buckle a little bit. Can we afford this dogleg severity across our completion? And in that moment, you already start talking with the service company to get their opinion. Can we pass through this doglegs planet, or we need to come back to the drilling engineers to be able to speak and try to mitigate? Can we reach the target with a different path in order to deploy completion? Because what is worth it to have a drilled well, but we cannot introduce the completion? So very important segment. If you go further, if you have a horizontal or extended reach well or multilateral well, as you can predict, this is just coming more complex in terms of completion, how we will interact with the reservoir, which kind of the tools we can put. Shell will run lower completion to complete the horizontal section and then come with the upper completion connected and so on. Going to basics here, natural assisted flow. I think everybody can get the answer here. If we have a reservoir pressure which can produce by natural flow, we have here an example of the one gas well or injector well. Very basic completion tools. We will have a pack, we will have a tubing, and if we have any other requirements in terms of corrosion, we can put some inhibition or great metallurgy to use. But basically, this is the most, let's say, simplest well if they are shallow. If we are talking about our reservoir, which is depleted, then we need to think to implement artificial lift. what I noticed that we have a specialist for the artificial lift, which assists completion engineer in order that the completion engineer compile this together and install in the final, let's say, well completion proposal. So this is very important that you have a good collaboration and good relationship with all stakeholders in your company to build trust and to build some networking which can help you to deliver this, because very often you are depending on their design, their time, and many times that the wells need to be passed through all these gate reviews very quickly. So you're also one of the tasks is to bring all of this from the stakeholders which you need to implement in your completion design, because those guys are specialists in, the example, ESP or circuit road pump, PCP pump, and they can give you the right artificial lift system for your application. Yeah. Nevertheless, completion engineer will select the perforation design. In that case, will assist with artificial lift for the Christmas tree, because the Christmas tree are more specific when we are talking about the artificial lift, because they are coming together with the artificial lift system. So in the artificial lift system, as I said, there is so many different systems which we can install depending on what we have available on the field. Did we have electricity on this drilling pad? Did we need to invest? How much need to be invested to bring this, if this is feasible to produce the well? Sometimes we have example, we need to build electricity grid to come to the rig, to the well site, which we want to drill the well, which is really a way of economics. And the well need to produce several years until become economical. So did we have gas available on the example on the platform which we can use for the gas lift, or we already, as I said, we have electricity which we can power ESP, PCP, or circuit road pump on, or we need to switch on the jet pumps in some cases. This is really dictating the facility availability for those occasions. Jumping on the number of zones, now we are collaborating a lot with reservoir engineer. Reservoir engineer will tell us that this well, what we will drill, having an example potential 2 or 3 zones or several zones which is planned to be produced during the whole well life. So in that moment, you need to start collaborating and see where I will place my packer. Shall I consider that I can perforate from the bottom to the top everything? Sometimes the governments of the states are having a very strict regulation how we can produce the wells. So they can restrict us and tell us that we cannot perforate everything and produce on one goal, because we need to pay attention how much hydrocarbons we produce from each zone. So they are bringing to us complexity which we need to answer. This is the task for the completion engineer. How we can segregate all of these and produce one by one and quantify. We can do it one layer by and then closing this one, opening another one, or we can do it maybe in the dual completion, producing 2 zones in the same time. Really depending on the completion engineer and the let's say the experience on the field and the crew in the production asset, how we can complete the wells. Of course, the best thing is always to look on your nearby wells. If you are, let's say, going to appraisal or development well, how they are equipped. Let's look in the history, how those wells produce. Did they have any issues during production? What are the key issues that you need to tackle for this? Yeah. So be patient. Do your research, even though if you don't get it initially with the documentation, try to get in touch with the production asset engineers in order to make a really good product for let's say, the final product. So what we can face here? number of zone produced. We can, as I said, we can make one completion for one zone, and then when this zone deplete, we will pull it out and complete with another set of the tubing in packer, and then perforate another zone. Or we can do through tubing isolation of the zone and open another zone. So it's basically it's up to you as a completion engineer to bring this complexity. Yeah, how you want to do it, what is the strategy, how much costs the workover. In some cases, workover can cost really a lot in some countries where the workover, let's say, rigs are not available, and then you need to book them a year in advance. Or if you are lucky to have your workovers crews which can execute those jobs, then the significantly less you will pay for those. So here we are coming with the economical components. How much I will pay in the future workover, and how I should complete the well to give the maximum value for my design. So, of course, those zones might have the same pressure, similar pressure, different fluid, which can cause plugging of one zones or creating some emulsion and complexity. So be careful if we have a multi-zone well that you need to produce at once, how you will manage this. Can you interact between zones? Did you plan to have a cross flow, so different pressure in the different zones? So here we are coming, really, you need to pay attention to the details, yeah, of each zone in time, how much they will produce, how long they will produce, and basically, again, look in the history how they manage those zones previously in the nearby wells. Sometimes you have very complex wells where you want in the same well bore, you want to inject in one zone, but to produce in another one. This is also possible, but it's, as I said, it's a little bit tricky and complex to do. When we come in here, number of zones, we also need to look, and this number of zone will affect our perforation strategy. Just to come back on the one of the tasks for the completion engineer, where we need to look how we will perforate the well. What will be the strategy for you to perforate the well to obtain the maximum, let's say, inflow of your hydrocarbons? If you have let's say, a bigger casing, a smaller tubing, that the gun which can pass through tubing can be very small, maybe will not be enough to connect your well bore with the reservoir, especially if you have problems during the drilling, and in this area you lost a lot of drilling fluids in the formation. So you need maybe additional, after that, the stimulation job. And as I said, number of zone can dictate many different things, but the best is if you can have an overview of historically nearby wells producing from the same zones. Let's say the topic about the reservoir and wellbore interface. This is very interesting. Sometimes I put this on the first place. As I said, this is not meant to be first, second place. These all inputs are very valuable for the creating a design. So whenever you start talking about the new wells, the first thing what I ask to the reservoir guy is the rock formation. What is about the rock formation? If it's a consolidated, semi-consolidated, which kind of the rock is there? It's a sandstone, carbonate, limestone. How he's confident that we can drill through this and don't have a collapse of the reservoir, or we have loose sand, which will be impossible for us to complete, and we need some sand control. Again, historically, if you have a data, great. If you don't have a data, and they should have something to give you, then you need to incorporate and try to give all the received data example to sand control engineer to give you advice what is the best solution for this kind of rock. Yeah. So basically we recognize the three basic variants here. We can drill through the rock if it's a very solid and leave open hole and produce like that. This is a really basic. We don't have any complexity there. But if the rock is semi-consolidated, then across this open hole, which is the picture in the middle, top picture, you can see that we install some sort of standalone screen, or we can go for gravel pack this. So gravel pack in the open hole to keep our small particles to don't come in the wellbore during the production. Or if we are confident that we can drill and then place casing, cement casing in place, and after that perforate. And if this is a strategy, then we need to align with our completion how this will look like. In some companies, also this decision to run liner hanger with the standalone screens will be also part of completion engineer decision. Yeah, but together with the reservoir, whenever we are talking about interaction with the reservoir and wellbore, this is very crucial that we get in touch with the reservoir and petrophysicists to understand a better reservoir, because not only the rock, the content of the hydrocarbons in the rock are very important for us. As I previously mentioned, the H2S content, CO2 content, this is very aggressive environment, and the fluid itself, the temperature and the porosity, permeability, this information will get in touch together also with a stimulation engineer. Because if we have very consolidated rock, most likely that we need some sort of stimulation, acid or fracturing job. Yeah, and this will dictate a shape through the reservoir, shape of the well, that meaning the well path. Going further, here we are coming to more completion area, where after gaining all this information about the production conduit or the flow path from the reservoir to the surface, this is the completion, purely completion decision. After all the pressures in the formation, the components of the hydrocarbons, we need to design some system containing of, let's say, here basically tubing and packer, which will isolate annulus. We need to come and select the tubing and packer which will withstand all these scenarios during the well life. So to select the tubing size, we need to have expected production, how much we want to produce, so to not put small tubing which will limit our well potential to produce, but also will look like in a mirror with the drilling design. So if we are designing the well which can produce 1 million of gas, we need at least 4-inch tubing there. And if our design is too small, we need to go back to the drilling desk and ask them to redesign to match the production estimation. Here, very sensitive topic is completion cost versus complexity and versus what we need. What I want to highlight here, basically, when we select the tubing size, we need to see and to run tubing stress analysis to see if everything will be compatible with all these different scenarios in the well. But as you know, the tubing, what we can order can be different metallurgy, can be like LAT, can be J55 grade, but metallurgy can be also chrome tubing if we have a CO2 or even super duplex material. So these materials will dictate the cost. Yeah. So if we are really having a corrosive environment, we will not put metallurgy which will be ruined in very short period of time, because if this happens, then we need to count on very complex workover, fishing job most likely, and a lot of lost money to recover the well. Because if we initially pay to drill the well several millions, and then we install very cheap completion, then the final product and the well life will not be so much, and then we will have more and more headache. So what we need to think here when we are selecting the tubing more. As I said, the tubing stress analysis is very important to validate our system. We need to design our well barriers in this respect that we can at least have a two independent barrier to be installed in the well. This is coming hand to hand with the completion tool selection, where we basically select landing nipple, which are flow control devices, which will be placed along the tubing on the strategic point that we can isolate our reservoir, and I put another one in order to prevent any hydrocarbon leak from the reservoir. Example, these well barrier policies are also going hand to hand with the state regulation, because also you can find in some state, like in Norway, they have their standards for the well barriers and the well integrity, where they really strictly says how design should look like and what need to be included in design. So you need to follow this. For the well intervention, why tubing is very important, because if you install some system in the well, you need to think what potentially can happen in the future. Can I go through tubing with a slick line, wire line, maybe to measure my production with PLT, or can I measure my condition of the tubing later on, measuring corrosion example, or if I need to go through tubing, coil tubing job to stimulate the reservoir with acid, can I access through my completion what I will put there? So even though somebody didn't require this, you cannot exclude that you need to do something in the well, at least slick line intervention. Because during the production we can have many other issues like paraffin accumulation. If you don't have any injection chemical to dissolve, then you will have often intervention with the slick line to cut paraffin to remove it from the wall of the tubing. Just as example. Or some wells need very often acid bath just to clean the perforation or near well bore. So you need to allow this kind of the operation inside your designed completion. When we move forward, we are coming to, I call it, functional capabilities. Yeah, functional capabilities are, in translation, the key completion component selection. What that means? On the picture on the right, you can see, let's say, the basic gas well completion in the well, which, as you can see, contain the tubing, contain the packer, contain subsurface safety valve, and sliding side door, chemical injection, side pocket management. So whenever is needed in your design that you can achieve some of the requirements, some goals which are coming from production, which are coming maybe from reservoir, to install the downhole pressure and temperature gauges to understand better reservoir behavior, you need to implement in your system, taking care that you will not make any restriction inside the tubing if possible. Yeah. So this is my recommendation. So not, I would say, is not very often that the state didn't regulate, example, where and on which well you need to put safety valve as a barrier. Safety feature which you will put in the tubing in case that something happened, that you can, some emergency shutdown, you need to do it for your well, and the press on the one button, you can close the well and close well downhole. In some countries, this is really defined that they require to put, example, in every natural flowing well, regardless how much production you obtaining from the well, they will force you to put. So this kind of regulation also going hand to hand with the completion engineer, that he need to understand and to know the regulation of the state in order to fulfill this requirement. Or this requirement might come from the operating company. Yeah? So operator defined already in his process and procedure where he need to put the safety valve, and then you need to follow. Of course, there is some exceptions, but nobody likes them. So if you need to do some exception because you know that the well life can be so long, you cannot avoid some requirements, or you can avoid for the certain period of time, and then you need to bring back them as per standard. So many of functional capabilities, which I call them like this, are coming. Example, putting the sliding side door in order to communicate with a circulation pad between the tubing and the A annulus. So in that order, you install the sliding side door. Maybe you are planning to do some killing the well in the near future, and instead of bullheading the well to avoid putting any interaction with the killing fluid and the reservoir, you will open SSD and kill the well with the killing fluid in order to recomplete the well. This is just an example. So these components are really up to requirements, up to your logistic, how you will do maybe workover in the future. You will put some of the tools there. Very important to put the flow control devices, which you can use for the several different purposes, which I will talk later on. So going to the, let's say on the end, I put for the end, but as I said, you can tackle all of these steps independently. Production technology discipline inputs. As I said, the completion engineer is not someone who will design everything. Yeah, he is in charge for the tubing design, completion tools design, packer design. But when we are coming on the production technology discipline inputs, I really have a good collaboration with my colleagues, and I really like their expertise, which can shape my final decision. Because you discuss with them, you see where this well is going to be, and then you adjust your completion for that one. So, example, if the well will be drilled across the, let's say, some geological formation, which is very tight and require hydraulic pressure stimulation, then you know how you will complete this reservoir section, and then you will insert maybe fracturing sleeves across, which you can do fracturing by compartments. And of course, then you are bring stimulation engineer, and then you bring reservoir engineer to better understand how often you need those sleeves, how many of let's say components and multi-stage fracturing job you are planning, because all of this will influence your upper completion and then the IDs in your tubing and the components. Very interesting interaction, I would say, is this interaction with the production technology engineers, like stimulation engineers, sand control, artificial lift, flow assurance. All of them, you need them input from them if you need to do some actions. Example, I will give you an example for the flow assurance. Flow assurance meaning metallurgy selection. If you have any problem with the scale formation, with the wax buildup, corrosion, erosion, or asphaltene, hydrates, slugging, gel formation. So all of these are problems with the flow assurance, where they do the modeling and tell you, yes, you have potentially this problem will occur, then we need to know how to tackle. Yeah, he can also advise you what to use, and maybe on this temperature and pressure, one option will not gonna work, but another one they have a good feedback. So be careful, collaborate with them, and get their input in order to shape your design. Yeah, artificial lift, straightforward. You will know on the beginning of the project if the formation can deliver or not naturally flow, then maybe you need artificial lift, maybe from the beginning, early beginning, or after some while you need to switch to artificial lift. So after going with all the inputs, all the critical components of the design for the completion. I would say that the completion engineer, as I put there, will looks like an octopus who is doing all of these things, gathering all the information, putting all together, designing one thing and looking for another, and then put a lot of compromises in order to shape the product, which should fulfill all the requirements. And you will say, how can be that we can answer all the requirements? Of course not. We cannot answer all the questions, but narrowing our design and compiling all the products which influence your design, all the stakeholders, you need to communication between them. So a lot of communication, a lot of going back to the desk to engineering something, especially if we have an unknown territory. If we have the reservoir which we never touch, we never complete, we never produce, then you need extra mile to input there in order to find the best solution. It's not always that 100% you will answer on this, but basically whenever you have more inputs, you can shape your product better. So going into the output, so in the, let's say, I call it deliverables. After your all inputs, you need to deliver the completion design. So you need to bring some deliverables. And as I said, from the beginning, those deliverables can be a preliminary designs, but when we come to the define phase, as you remember our journey of the completion engineer and all those phases, when we come to the define phase, we need to basically to finalize our design and to validate design. So to do all of this, you need to go through the several of them, as I state here: tubing stress analysis, tubing selection and design, metallurgy selection, well completion tool selection, completion fluid selection, Christmas tree selection, perforation design, well barrier design, and all of those are compiling in the well completion program and the single delivery for the well completion engineer on the end of the, let's say, planning phase. So here we will touch the details of each of deliverables and how it looks like when we are going through this, let's say, journey and all the deliverables items. So as I mentioned on the beginning, the tubing stress analysis, tubing selection, there is many of the softwares on the market, to not list them here, but most usable one for the, let's say, use it in the tubing size selection in comparing with the production estimation. It's like a Prosper one, and the tubing stress analysis, there is like a Wellcat, the Pipe Sim from Schlumberger, and Oliasoft launch another software also for the tubing stress analysis. So there is a plenty of softwares which you can use in order to simulate different scenarios during the production with your proposed completion design. And basically, you stress your system with the different scenarios. In some cases, example, in my company, we define all these scenarios as a standard scenarios which we need to apply on each of our simulations. So basically, you simulate the well during the running hole the completion, during the pressure test the tubing, pressure test the annulus, possible leak in the annulus, tubing evacuation scenario. If you have any stimulation, you put stimulation, killing well to in case that you need to kill well, and so on. So many different scenarios, occasions, and then you stress your selected completion and tubing and see if everything will work, including the tubing connections. You know that tubing connections, basically we can divide them in API and premium connections, where the API connection can withstand a fluid, but the gas can leak through them. So we have a premium connection, which are gas tight connection for the gas wells, which on the tubing connection we prevent a gas leak. Yeah. So As you can see here on the right picture, so the selecting the tubing, this is the primary all what you need to select: the size of the tubing, the weight of the tubing, the grade of the tubing, this LAT, and metallurgy. Example, I put here 13 chrome. VAM top, I just put select one of the premium connection. So all these need to define by completion engineer. If you have any special requirements going to the field of the special wells where we need to insert um, example tubing which is a coated inside, or vacuum isolated tubing if we have a really hot environment, then this is additional stuff which you need to include. But basically, you build your stuff according to all the information that you get. You stress here in the tubing stress analysis, and then you see your interaction tubing and packer with your well construction will work or not. And if not, you need to see where is not working and what you can change. After you finalize this, very important thing is that if something happen in the future or during the well production, the guys will come back to the well completion engineer and then see if he simulate this or predict this or not. Yeah. So he need also to realize what are the limitation and put this here in the design. When we are going to the metallurgy selection, we are looking on metallurgy of our tubing and metallurgy of our completion components. So as you can see on the really right, you can see how it looks like the tubing in the H2S environment, how the H2S corrosion looks like inside, how the CO2 corrosion looks like, or when you inject the steam, how this will affect your metallurgy and tubulars. So it's very important for you to select the proper metallurgy. As a completion engineer, you are not, most of the time, let's say like this, most of the time the metallurgy selection is not fully responsibility of the completion engineer, but the completion engineer, as I said, need to come with the preliminary design. You need to have a clue which kind of metallurgy will work under your environment. And if the environment doesn't include H2S, CO2, or any environment which will affect your metallurgy, then you can go straight forward for the low carbon steels. But if you have deep well with the high temperature, with a possible CO2 and H2S content of the fluid, then you need to go to your laboratory, or you need to engage consultant, or you need to engage the service company providing completion tools to simulate your environment and to give you advice which kind of metallurgy you should install in your well. The best thing is that you have laboratory with your operator company, which you can compare with service provider recommendation, and then you match this and see which is the best metallurgy for you. As I said, metallurgy selection also can have two phases. You can go for the best metallurgy, which will cost you most probably the comparing with the low carbon steel a lot, but then you need to go to the flow assurance engineer to see how you can maybe install low carbon steel with chemical injection, which can protect your tubing further on. But then you need to count on OPEX, where you need to pay these chemicals basically to inject every day there. So this is a position of the completion engineer where you need to also to look on the cost, which is the best. We know that if we put everything singing and dancing, the cost will be up to sky and nobody will approve your project. But if it's really needed that you can demonstrate that the higher metallurgy will affect your well projected life, then it's okay. Yeah? Then you can count on the better metallurgy, which you can eliminate complex workover, failure of the tubing, leak, loss of the production, and so on. So once again, not really your decision, but you are really involved here in the early stage to give a preliminary methodology selection with a preliminary cost, which you can fine tune later on with specialists. When we are coming on the Christmas tree selection, I will just highlight that the Christmas tree selection is purely completion engineer task, but only if the well is producing by natural flow. If it's artificial lift, as I mentioned, the artificial lift systems are coming with the different Christmas tree systems which will fit together. So looking here only on natural flowing well, we can have a different setups. For the subsea wells, we have a separate engineer only for subsea Christmas tree. Well, the completion engineer job is finalized until tubing hanger, and everything which is above, it's his responsibility, the specialist for the subsea trees. But if we have a dry trees, which can be mounted on the platforms, can be mounted onshore, so responsibility to select the proper Christmas tree, considering the flow, considering the environment, temperature, and as I state here on the right side, as per API 6A specification for the wellhead and Christmas tree, you can find these pressure classes, temperature classes, material class, and the product specification level, which you need to define to know to select the proper Christmas tree, which will work and not get damaged during the production. Of course, when we have safety valve in our completion, then when we have a corrosion inhibition or any other chemical inhibition, maybe downhole pressure and temperature gauges, then we have a different control lines, electrical lines are coming outside of the tubing, and they somehow need to go out of the well, passing by the tubing hanger. So tubing hanger is very important, how many control lines we have there, and then tubing head spool with the tubing hanger will be responsibility of the completion engineer. So be careful here, select, and basically the complexity are starting already here, as the tubing hanger is a component which have the most impact of tensile strength in the well, because the critical point in our completion is the first joint below the tubing hanger, because we hang all our completion at that point. So the most forces will be created below the tubing hanger. So this is very important component. I just wanted to highlight that very often this can be mismatched with something, and we can create very, let's say, not convenient situation for the completion engineer if design was not meant. But the whole Christmas tree is a package which will be installed together with tubing head spool. As I said, 99% is a completion engineer responsibility. I will stick with this completion design over these deliverables that you can easily track one by one how we progress. So, well, completion tool selection. As I said, the main components, tubing and packer, is selected in your design, but you have different ones which need to answer the task which you need to accomplish. As I said, if we put low carbon steel, maybe you need chemical injection. Here we are talking about the safety. If you have a natural flowing well, if something happened on the surface, Christmas tree start leaking, we have somebody hit the flow line, and then we have uncontrolled flow from the well. To stop this, we install safety valve. We call it the tube. Example here, we have an example of the tubing mounted retrievable subsurface safety valve. So we control this device from the surface in order to open and close our well flow. In emergency cases, we are not using that for this purpose to open and close. We have Christmas tree. So here you can see the components. which basically we install on the natural gas flowing well, meaning safety valve subsurface, but on the Christmas tree, we more often have hydraulically operated valves, one as a gate valve and another one as a master valve. So this is how we can control in this emergency situation. We can close the well in a couple of seconds. Yeah, this can be also hooked up on our CADA system, and then you can do it even from the office. You can control the well. Going further on our well completion tool selection, as I mentioned several times, sliding side door, where we are using sliding side door. We are using in case that if we want to kill the well, to not expose our reservoir with the completion fluid or killing fluid. In case that we have several packers and several layers which we need to produce one by one separately, we can use sliding side door to open one layer and to close, open, close. So this is in these situations, as I put here, the selective production or single selective completion, we can use sliding side door to control our inflow from the different reservoirs. And of course, if we have any kind of the selective injection and you want to control production from some phase or injection to another layers, you can use this device. This device is a pretty much standard device for all the completions and used very, very often in the completion design. Going further, as I already mentioned previously, if we have any kind of the expected corrosion and we want to protect our tubular completion tools, we can inject chemicals which can make a protective film on our tubing during the production, and basically the bare metal will not come in contact with the produced fluid, and we will lower much more the corrosion in our system. So these components are injected through the chemical injection mandrel, where we have one piece of the completion tools and the injection valve connected with a very small control line coming to the surface. And basically on the surface, we inject chemicals which come inside the tubing and then coming in the flow stream. But not only on the corrosion, we are using this in case of any flow assurance issues. If we have asphaltene, wax creation, hydrate, scale, we can pump different chemicals to tackle different issues. Or in the really, let's say, end of the natural flowing phase where we have a lot of water coming, slugging, we can inject chemicals to make a foam and basically prolong well life. For the permanent downhole gauges, as I mentioned, we can monitor reservoir very, very closely. We can put the pressure and temperature gauges basically very close to reservoir. And to do that, we are using almost the same system, the mandrel with mounted pressure and temperature gauges, which can measure inside the tubing or outside the tubing all these parameters. Or we are going on the very fancy things using a fiber optic cable mounted on the externally on the tubing, basically, which will give us a much accurate pressure and temperature values. So moving forward, as I said, the main components as a tubing and packer in the completion design, now we are coming on the packer, very important component of the completion, which basically we need to select in order to isolate our reservoir from the rest of the casing which we install as a production casing. Why this is important? You have only one production casing. If you expose casing to the pressures, to the reservoir fluids, you can create corrosion for the planned well life, which can be 20, 30 years. I can tell you in the country where I'm currently working, we have some wells from 1950. So the wells, more than 70 years, they are in operations. So if you expose your casing, definitely you will damage, and the well will not be under the, let's say, well integrity issue will appear. So in order to prevent exposure of the fluid inside the casing above the packet, you install this and isolate your reservoir. And then you changing a tubing and packer more often, but your production casing is always there. So you need to take care about him. In this case, there is a different packers on the market. I divide them here really basically on mechanical packer, which we can set rotational by rotating the tubing and slack off on the packer, or pulling the packer up. Will set slips and the rubber elements, which will isolate our reservoir from the rest of the production casing. Or we can use hydraulic set packer tubing connected. Some packers are coming in the system that we first install the packer and the tailpipe in the well, and then upper completion, if we are coming with the complexity like on this picture, coming with control lines, with a safety valve, with a chemical injection, then we can do it separately, run and connect with the packer. In that case, we are using a seal bore packer configuration. Of course, there is also special application when we have a very complex wells, or we have, for example, ESP pumps, then we can use this dual ESP packer bore type of the packers in this case. Regarding this seal bore packer, we also have here the category that we can run the packer and then connect with the upper completion with the tubing with permanent latch, which when we latch together, it will be one system, but is not meant to be, let's say, moving up and down. So during the production, during the injection, you can imagine our metallurgy will shrink or elongate. And in these events, if you want to accomplish that your upper completion is just traveling inside the packer, then you need to use a different system. I mark it here with greens. So seal units, locator seal assembly. So all this will give us opportunity to connect upper completion with the packer, but in the future, whenever we want to pull our completion, we just need to pull up, and this we can easily replace. With the packer in place can be for the longer period of time. Going to isolation plugs, memory gauge. Basically, we're using a landing nipple to put any kind of flow control devices. Flow control devices, just the words itself is self-explanatory. So this is the component where we can use for different purposes, but the main purpose is to control the flow. We can choke the flow, we can put the plug to isolate our reservoir from the rest of the well. We can use it for plug to test the tubing to see if the tubing is okay, or we can set the plug to set these hydraulically set packers. We can install the memory gauges on the slick line. We can put some intelligent plugs. So many different things we can use with this landing nipple. Basically put different devices to do something in the well, to monitor, to record something, to isolate. So they are very handy. And a part of the landing nipple, this same profile contained in the sliding side door and in safety valve. So whenever we want to put the plug as a barrier, we can do it not only in landing nipple, but by default, sliding side doors and the safety valves are coming with this feature. When we come to this one, which is really, for me, very interesting part of the decision how we will complete the well, is a reservoir interface. As I mentioned before, this reservoir interface, in early stages, you discover what is the rock characteristic in order to know what kind of the completion we will put across the reservoir. If we need something special, if it will be long horizontal section that we need to stimulate because the rock is very tight, or if we don't plan any stimulation, but due to the horizontal shape, we are expecting the water breakthrough, example, on the heel more often than in the toe. So we can put devices which can, example, inflow control devices, which can mitigate your flow if water comes, to choke the water, but to let oil to flow much with a higher rate. Or we can put devices that when we record the water breakthrough, we can go investigate where, and then we can basically close this production section. So if we need to do any kind of stimulation, I put here an example of the high pressure stimulation multi-stage frac completion. On the really bottom picture, you can see that the lower completion will be made from, let's say, liner hanger packer with a liner hanger with a lot of isolation packers and frac ports, which we can frac from the toe to the heel, and basically connect the reservoir much better for much better inflow. Going and jumping on the completion fluid selection, very important for the completion engineer to select the fluid which can stay inside the our A annulus for the longer period of time. A annulus is the place between the production casing and the tubing, where when we run the completion, we are running in the completion fluid. So this fluid need to be really clean, containing a lot of other components as corrosion inhibitors to prevent any corrosion, because it will stay longer period of time. But before we pump and exchange any kind of fluid with the completion fluid, we need to run a lot of wellbore clean out tools. We can do it in one run, put a lot of magnets, brushes, as you can see here, to scrape all remaining fluids from the previous operations, like cementing jobs, and basically to prepare our internal well very clean. And then in the same run, we can exchange the fluid with the completion fluid, which, by the way, having a also feature that will not interact with the after we perforate the well, because after we perforate, this fluid will be exposed to your reservoir. So you don't want to have any emulsion or any bridges which will decrease your production rate, which you estimate. So some people take this not very seriously. I said it's really something that you need to pay attention. Also, look behind, look best practices, what you use on the field, on those production layer which you want to perforate, in order to not make any complications. When we come to the perforation design need also a lot of interaction with rock matrix. That means with the reservoir engineers, that you need to obtain a lot of information like permeability, porosity, pressure, temperature, that you can give to the service provider all of these details, and they will run simulation of perforation for you. I will just say that we have a basic division between the deep penetration type of perforation charges, which we use to penetrate through the casing and inside the formation, and we have another type of charges called big hole. Deep penetration we use when we have a natural flowing well without sand control, but the big hole we are using to create a big hole on the casings, which we need to run sand control screens and to do gravel pack and to have a much bigger inflow inside. You can distinguish that from the words. Deep penetration will penetrate very deeply. Very deeply is not more than couple of 10, 20 inches, maximum 30 inches, depends of the charges and the weight of the charges. So what we can use here, we can use casing guns, which are run on the wire line through casing, basically together with TCP, tubing conveyed perforation. Those charges can be much, much bigger. If we are running our perforation gun through already installed system through tubing, then you can assume that this gun can be a much smaller, charges smaller, so that the penetration inside the reservoir will be smaller. Yeah, and the let's say the mystic about the perforation guns, I very often talking with the guys from the asset, they considering that perforation is just making a hole on the casing and nothing else. I can tell you the perforation is really complex step which need really precisely to be designed, because more often I saw examples that people don't taking this seriously, and then when perforating they don't have an inflow, and then they can move to another layer, leaving this layer not produced just because they pick up the wrong gun. Coming close to the end of the deliverables, the well barrier design, more often when the well integrity now is a big player in the game, and then we need to respect some rules, some state rules, and to follow standards. You need to think about where you will place your barrier in case that you need, example, in emergency cases that you need to isolate reservoir. Why this is important? I will give an example. Recently, I found a case that we produced a well where the reservoir pressure is much higher than pressure test of the production casing which we made. During the production, we identified that the tubing is leaking inside the A annulus, and the huge pressure which was applied in the A annulus can jeopardize A annulus to burst and to come to the catastrophic event. So in that moment, we need to react fast and to put the plug below the packer to isolate reservoir. If we didn't design our completion in order to have this landing nipple really on the bottom of our completion below the last packer, we couldn't succeed this one. So really important to understand your well barriers. There is a lot of softwares now on the market is assisting you for this one, and basically every well completion program on the end must have well barrier design per each well step. So if you are running your completion, when you set your completion, if you do the stimulation job or well intervention job or production, you need to have for each of those phases one well barrier design in order to justify that you have two independent barriers in any moment. We are talking about the natural flowing wells. If we are switched to the artificial lift flowing wells, the rules are not very strict, and basically because if you stop with artificial lift, your well will most likely die, and at least you need to have one barrier, and the second barrier can be a fluid which you will use to kill the well. Going on our last slide for today, I will compile all of these things, and we will say that all these deliverables now, what we are talking about, which are responsible of the completion engineer, need to be put and compiled together with very detailed operational steps into the well completion program, which will be the ultimate technical proposal with economical overview of the completion, which need to be approved by technical authority for the technical, but also for the project management economical part. So I can see some completion engineers doing very well jobs. Some of them, they're putting a lot of, let's say, safety factors which need to be reviewed and re-evaluate, because sometimes even though completion are like 4 to 5% of the total value of the new well, we need to justify cost of putting maybe very expensive tubulars. Just giving a small example of selecting the tubing, which is a low carbon steel, and if you want to put very expensive chrome tubing, can be 5 to 10 times more than the low carbon steel. So all these together, adding maybe downhole gauges, maybe permanent downhole gauges, some fancy equipment can really significantly increase cost, which you need to defend in front of the technical authority and project management gate reviewers. But if you are refused, you need to go back on your desk and redo the job. If you come to the end that this design is really fit to purpose and you cannot decrease cost, which in nowadays everything is now eyes on the economical parts, we need to accept maybe that the well which we plan to drill and equip can be really much more expensive and not economical in terms of the revenue. So this is in very short the journey of the completion engineer and his task and his jobs, what he need to gather, what he need to deliver. I spent the last 12 years with the completion discipline and the well integrity discipline together, and I think this is the most exciting part of my career. I'm technically oriented person, and for me, any challenge that you put, I would like to make better. So I'm always happy if we find a solution which will work for our wells for the longer period of time, which we always do. So, Nikhil,